Institute Christmas Lectures, Lecture 4, Games and Evolution. 20 seconds. Nine, 8, 7, 6, 5, 4, 3.
So far, we've been talking about pure mathematics. That is the nature of mathematics and the art of proving theorems. For the last 3 lectures, I want to shift emphasis slightly towards applied mathematics, that is the mathematics of nature, and talk about the art of modeling. By a mathematical model, I mean you take something that's difficult to understand, and then you try and abstract the essence of it into mathematical terms, and then you fool around and prove some theorems and get the answer and translate this back into scientific language, and then that will enable you to understand the phenomenon and predict the future. Well, one uses mathematics to model things in all branches of science, of course, and all the things one models are very different, but surprisingly, the style of modeling is very often very much the same, and it depends very often upon whether the thing that you are modeling is continuous or discrete. Do you know what I mean by discrete? Discrete is the opposite to continuous. Discrete, spelt with an ETE at the end, means the thing is made up of separate parts. And so what we can think of is we can think of discrete things and continuous things behaving discretely or behaving continuously. And so what I want to do is to give you examples of each of these 4 types of phenomena. The simplest one is discrete things behaving discretely. So could we have a dice, Bill? You see, this is the epitome of a discrete thing behaving discretely. A dice is a discrete thing. And when you roll it, you never bother where it actually lands. All you're interested in is what number is on top. There's number 1, actually, at the moment here. And there's exactly 6 ways. And so it's a very finite problem. And the corresponding style of mathematics to analyze this kind of behavior is probability and game theory. And indeed, it was Pascal and Fermat first invented probability theory in 1654, around about that, to handle the very business of games of dice. So that's discrete things behaving discretely. In a moment, we'll come back to the dice and actually play some games. But I want to try the next one. This is discrete things behaving continuously. Now, the typical discrete thing behaving continuously is a pendulum. You see, these 2 pendula are discrete things, and if I set one swinging, it's behaving in a continuous way. And if I want to work out the period of swing, then the typical style of mathematics to use is calculus and differential equations. And that's exactly what Newton invented calculus and differential equations for, because the classical example of discrete things behaving continuously is, of course, planets going around the sun. And Newton was faced with a problem that Kepler had just discovered, that the Earth and the other planets went round the sun in elliptical orbits with the sun at the focus. Now, this was an extraordinary discovery because, I mean, it's so unnatural. Why should the sun be at one of the foci and not in the center? And the asymmetry of the orbit is very tantalizing. And Newton did 2 things. He invented his famous law of gravity, that the attraction of the Earth and the sun should vary as the inverse distance squared. And then he invented calculus as a tool by which to convert that law into the geometrical orbit. And thus, he was able to prove from that single hypothesis that the planet should follow elliptical orbits. Well, the next idea is continuous things behaving continuously. And a typical example of that is water, the actual motion of water. So if I make some waves, then you can see the water waving. Water is a continuous thing, and the behavior of the waves is a continuous. So that's a continuous thing behaving continuously. And in the next lecture, we shall actually look at some musical instruments and see how waves run along the musical instruments. And finally, the last thing is continuous things behaving discretely. And that, in some ways, is the most mysterious of all. I mean, after all, why should continuous things choose to behave discretely? Now, I'd like to have does anybody play the trumpet? Have we got a trumpet? Yes, we have. Great. Can you come out? Would you like to come and play? Here's a trumpet for you. Can you play this trumpet? Very good. Can you get a different note on it? And I'll play one too, and see if we can play a duet. Thank you very much. What's your name? James. James. Well, I don't know whether you heard it in our trumpeting, but the extraordinary thing is when you press your lips together more and more, gradually more and more, the note, instead of rising gradually, it stays the same and then suddenly jumps up to a harmonic and then suddenly jumps up to another harmonic. Now, why should that happen? That's very peculiar. Well, the harmonic analysis is the explanation of why that continuous thing should go in discrete jumps, and that's what we'll be doing in the next lecture. And the theorems about continuous things behaving discretely are some of the most beautiful and the most subtle, because the phenomena that they describe are some of the most difficult to understand. And in the last lecture, we shall be doing catastrophe theory, which is another example which explains how gradually changing forces can cause something to behave discretely in continuous jumps. But today, I want to go back and play some games with the dice, because they're the finite things, discrete things behaving discretely, are the easiest to understand. Now, who wants to come and gamble? There's an eager young gambler. And in the red jacket there, we haven't had you before, have we? Come down then. Now, we're going to have a banker and a gambler. Which do you want to be? Banker. Banker, okay, you come around here. And you're the gambler. So here's your money. There's some money for you. And that's ones, and they're tens. And here's lots of money for the bank. Oh, you can't have that. Right. Now, I don't know whether you've actually seen have you looked at the £1 note? Mm-hmm. You know who's on the back of the £1 note?
Britannia. Or Newton.
Newton, that's right. Newton. He's actually got a drawing of his famous theorem, the ellipse, and there at the center is the letter C for the center of the ellipse, and there at the focus is the letter S for the sun. And now I'll tell you a joke. You know the chap at the Mint, when he actually drew this, he looked at he took this picture from Newton's book and he said, we better touch it up a bit. And he actually put the sun in, but he goofed. He put it at the center. And so, Newton must be turning in his grave, because he got the main theorem wrong. But our money is proper, good and proper, because we've put the sun, if you notice, properly at the focus. Right. Now, you're going to roll the dice. Well, it's a bit difficult to roll. I think this time we'll have to ask you for something smaller rather than something bigger. Thanks. I'll explain the game that you're going to... We'll just have one dice to start with. So you stand over there, and you're going to roll the dice towards us, and I'll tell you what the game is you're going to play, is you're going to bet you'll get a 6, you see. Now, when you roll the dice, you're going to lay out a £1 stake, like that you're going to get a 6. And, of course, you'll only have one chance in 6 of getting a 6, and so, on the average, you'll win once and lose 5 times. So the odds against you are 5 to 1. So you say to the banker, now, if he's putting a £1 stake, you'll give him £5 when he wins, won't you?
Yes.
No, you won't. I mean, the banker says, I've got my overheads, I've got to pay my salary, and so for income tax, I can't afford that. I must lower the odds. You're only going to give him £4, aren't you?
Okay, yes.
No, he's not. He's only going to give you £4. So the odds are stacked against you. Okay, roll the bone. 3. You got 3, so you lose your stake. Try again. Another stake. 3. Lose your stake. Try again. So, try again. 1. Lose your stake again. Well, as you can see, it's not a very good game. But so what I want to now work out is exactly how much you're going to lose. So thank you very much. Thank you very much. So the theorem we want to prove is that your expected loss is 1/6 of a pound per throw. So that really means you're not going to lose exactly 1/6 of a pound every throw. It means that if you played 600 games, then on the average you'd expect to lose 100 pounds. And if you played 2 games, that is to say, if you rolled 2 dice at once, you'd expect to lose 2 times the 6. So you'd expect to lose 1/3 of a pound. So I must prove that. You see these? This little square here is called the payoff matrix. And here's you, and here's the bank. And this is what happens if you win a 6, and this is what happens if you don't win a 6. And so if you win a 6, of course, you're going to get +4. But if you have no 6, you're going to lose your stake, which is -1. And then the bank has exactly the opposite. So it's going to lose -4 if you win, and gain 1 if you lose. Now, the next thing to look at is the probabilities here. The probability of getting a 6 is just 1/6, and the probability of not getting a 6 is 5/6. And now we can work out our expected gain because we multiply your expectation by your probability, so you get 4/6 for that many times, and then -1 5/6 of the time, so you get -1 times 5/6, which is -5/6, and 4/6 minus 5/6 is equal to -1/6, and that is your expected gain, so that's the proof of the theorem. And the bank, of course, has exactly the opposite. He expects to gain +1/6. You expect to lose 1/6, and the bank expects to gain 1/6. Well, that's quite a simple game, so what you say to yourself is that I'm on a losing streak. Perhaps I ought to insure myself against the losses. So this time I need 3 volunteers, so I need an insurance man too. Now, who can be? Did you come up last time? Yes. Well, we won't have anybody. Those who came up before, put your hands down. So would you like to be the banker or the gambler? Yes. And with a striped red shirt. Would you like to be the insurance man? And now, who shall we have for the... yes, why not you come? Yes, that's right. You come and be the gambler this time. And you're going to gamble with 2 dice. Now, where's the banker? Come round here. And there's your money. And here's the insurance man. The insurance man, we better give him lots of 10s. He's got to be a rich man, you see. There's your... and you want a few 1s, so we'll take a few from the bank and the gambler. There you are. There's your money. You keep it here. That's right. Now, so before you get, we'll just play with 2 dice. You see, with 2 dice, each time you're going to lay 1 stake on each dice. So throw the dice. Oh, yes. Well, why don't you stand over there and make a good big throw? But will you? A 1 and a 5. Lose both that. All right, have another go. 2 stakes. A 5 and a 1. Lose them again. You're not doing very well. Go on. 2 1s. Oh, lose them again. Well, it's quite obvious that you're on a losing streak. So what you come along to the insurance man, and you said, when I was playing with just 1 dice, I was losing 1/6 of a pound per throw. Now with 2 dice, I'm losing 1/3 of a pound per throw. And when I was just throwing 1 dice, I expected to win 1 game in 6 and lose 5. And the odds were against me were about 5 to 1. And now, with 2 dice, I expect to win 1 game and in 3, and lose about 2 games in 3. So the odds are against me about 2 to 1. So why don't I insure myself with you? Why don't, every time I win, I'll pay you £20, and every time I lose, you pay me £10. You see? So you insure me at odds of 2 to 1. So what will you say? Will you take that?
No.
What's in it for you? That's quite right. You'll say, I want more than 2 to 1. So you say, all right then, every time I win, I'll give him £21. Will you accept that?
No.
Won't you accept that? What will you accept? £22? No, 20. Accept 21 pence. Okay, he'll accept £21. All right, then roll the bones. Put out your stake. You've got a 1 and a 2. So you lose your stakes, but you'll have to pay him £10. That's right. Okay, roll again. Put out 2 stakes. A 3 and a 5. Lose? Oh, another £10. That's great. Go on. Put another ones out. Double 3. Another £10. That's great. Go on like this. Another 2. Yes. A 6 at last, a 6 and a 1. So let's see, now you lose that 1, but you have to pay him 4 for his, 4, that's right, for that 1. And then you have to pay him 21 now. That's better. Okay, thanks very much. Well, now well, you can see, overall you made a gain, didn't you? Well, you'd better have £11. That was your winnings. Okay, right, thank you very much. Here you are, £11 for you. And you've got your £11 for the bank, huh? Yeah, bye-bye. Well, now, the astonishing thing was that although the odds were loaded against him, I mean, the banker had given him odds against him, and the insurance man had given him odds against him, he seemed to be winning. And actually, here is the theorem. This time, the theorem is your expected gain is 7/36 of a pound per throw. He's actually expecting to gain. Now, this is pretty amazing. How does that happen when the odds are loaded against him? So that's our next theorem. We'll have to prove that. So we've got a bigger payoff matrix now. So first of all, we'll do the bank. The 3 possibilities are a double 6, 1 6, or no 6. And if he gets a double 6, of course, the bank has to pay out £8, so it's -8 there. If he gets 1 6, the bank pays out 4 on 1 dice and rakes in 1 on the other, so that it pays out -3. And if he gets no 6 at all, the bank gets the 2 stakes, so that's 2. Now we'll work out the insurance man. He wins here, so the insurance man gets £21. He wins here, so the insurance man gets another £21. But if he happens to get no 6 at all, the insurance man pays out -10. And now we can work out what you get. If you get a double 6, you have to pay out £21 to the insurance and collect 8 from the bank, so your net result is -13. if you get 1 6, you have to pay out 21s, you only get 3 from the bank. So you do even worse, minus 18. And it's only when you get no 6 at all do you actually collect £8, £10 from the bank and pay out 2. So it still looks pretty amazing how you can possibly win with this. But the next thing to do is to work out the probabilities. Now, what are the probabilities with 2 dice? Now, here's a 6 by 6 diagram. Down here is 1 dice, and down here is the other dice. And these give you all 36 possibilities for the 2 dice. Well, there's only one double 6 there, and so the probability of getting a double 6 is 1 in 36. So this probability is 1 in 36. Now, what's the probability of getting no 6s at all? Well, on this dice you'll have to have 1 to 5, and on this dice you'll have to have 1 to 5, and so we've got a 5 by 5 square of possibilities when you get no 6 at all. And 5 times 5 is 25, and so in this space here I have to put 25 36s. Now that leaves me with to count up the times when you get exactly 1 6, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the probability of getting exactly 1 dice is 10 over 36. Well, we can now work out your probability times your expectation. So it's going to be in terms of 36s. So 1 time you're going to get minus 13. 10 times you're going to get minus 18, so that's minus 180. So altogether that's minus 193. And then 25 times you're going to get plus 8, or 25 times 8 is 200, so you're going to get plus 200, and so 200 minus 193 is plus 7, so your expected gain is 736. So that proves the theorem. But it leaves open the question, if you're gaining, who's losing? I mean, how was it when both the odds were against you that you managed to gain? So we better work out the bank. See, the bank, he says 1 time he's going to get minus 8, 10 times he's going to get minus 30, so it's minus 38, and 2 times he's going to get, or 25 times he's going to get 2, so that's plus 50. So you've got plus 50 minus 38 is plus 12, so he's going to get 12 36ths. So that's 1/3. Well, that's what he expected to get. You know, when playing with 2 dice before, he expected to get a third. He expected with 1 dice, he expected to get a 6. With 2 dice, he expected to get a third. So it must be the insurance man. So let's check him. Let's see the insurance man. Let's work it out over here. This is 21. 1 time he's going to get 21. 10 times he's going to get 21, so that's 210. So he's going to get plus 231. And then 25 times he's going to get minus 10, so that's minus 250. You see, and so minus 250 plus 231 is minus 19. So there he is. His expected loss is minus 1936, of which 7 go to you and 12 go to the bank. So that explains it. Well, now, how did the insurance man get himself into this predicament? And he was very wise. He said he wasn't going to accept it. Did you know the answer? No, you didn't. Well, you had the right intuition, I must admit. Because, you see, what happened was, when I was doing the spiel about telling you the odds were about 2 to 1, they weren't really 2 to 1, because we can now really work out what the odds are. You see, the odds of you winning, the odds of you losing are 25, and winning is 11. So really the odds were 25 to 11, which is more like 2.3 to 1, not 2 to 1. You see, so when you stepped up the odds to 2.1 to 1, you were still below the real odds. You see, so you still had the edge. He thought he had the edge, but in actual fact you had the edge because it was 2.1 to 1, you see, because the real odds are 2.3 to 1. Well then, having done that, having got those odds, then you exploit it like mad. You step up the bid with the insurance money, You see, you bet with him a much bigger sum than you bet with the bank, so that your winnings on the insurance outweigh your losings on the bank. And that's how you can gain. Well, of course, this explains why no insurance man worth his salt ever insures against gambling losses. But you can see this technique of using a payoff matrix and probabilities and expected gains, once you get into the more difficult world of business, where you are trying to assess market probabilities, and you're making decisions and having to weigh up insurance and costs and so forth, well, this kind of technique is extremely useful in working out, helping you what to decide. Well, I want to play another game now. This one is called Doves and Hawks. This time we're going to have a little 2x2 payoff matrix, and I'm going to imagine a battle between you and an opponent, you see, and each of you can either play a dove or a hawk. Now, these are your two strategies, hawk and a dove, and these are your opponent's strategies, hawk and dove, but of course you don't know which he's going to play. That's the problem. And you don't know what probability he's going. He might be with probability half here and a half here, or he might always be playing the hawk. You see, that's the uncertainty. So it's a bit like the other problem, where, except that this time the probabilities are unknown. Now, this payoff matrix represents the score to you. When you play the hawk and he plays the hawk, you both get -2. When you play the dove and he plays the hawk, you get 0. So what I'd like to do is I need some volunteers to come out and play the dove and hawk. But does anybody know the rock, paper and scissors game? You know it. Okay, you come out then. Anybody else know the rock, scissors, paper game? You know it, in green there. Yes, you come out. And let's see, you know it, you come out. This is going to be, come round here. Now, you two stand here, you see, and you watch carefully what I'm going to do, because later you two are going to play it, but first of all, I'll start it with, what's your name?
Anne.
Anne. I'm going to play with Anne, and then what's your name?
Timothy.
Timothy?
Owen.
Owen. Timothy and Owen. Okay. Not Owen Clark.
Yes.
How do you do? Now, Anne, how we played the game, first of all, we point at each other. You've got to point at my eyes. Go on, point at my eyes. That's right, you see. And now when I count 1, 2, 3, we're going to beat like this, like a conductor. 1, 2, 3. Now, on the game of 3, on the same 3, you've got two possibilities. You're either going to put your hand out like that, sort of a peaceful dove, or you're going to put your fist out like a powerful hawk, you see. So, try it. When I say 3, I'll say 1, 2, 3, and then you go. Ready? Point at my eyes. Ready? 1, 2, 3. That's right. Only you've got to keep a poker face, you see. You mustn't tell me what you're going to do. Otherwise, I can beat you on this payoff matrix, you see. Do it again then. Gaze into my eyes. Point. Don't reveal me. That's right. Point. Ready? 1, 2, 3. Oh, you were a hawk that time. You beat me, you see, because you were a hawk. You played 6, and I played a dove. So if we look off the payoff matrix here, you see, you played the hawk, and I played the dove, so you get +6, and I got 0. Well, have you two boys learnt the game?
Yeah.
Okay, now we'll have you playing, and we'll have Anne scoring. So you were Owen, and why don't you, yes, you stand there and play it, you see, like that, and then Anne will score. You're Owen on this. You better come this side, because I've written Owen on the board. That's right. Because otherwise she'll get confused. So will I, actually. Timothy. Right. You got the chalk now. Ready? Okay. I'll count. Wait, I'll count. Point at his eyes. Poker face now. 1, 2, 3. Oh, 2 hawks. -2 to both of them. Now, point again. Ready? 1, 2, 3. Ah, he's a hawk and he's a dove. So 6 to Timothy, that makes him keep the, that's right. And a 0 to Owen. Point again. Ready? 1, 2, 3. Oh, 2 to each. They're both doves. Ready? 1, 2, 3. Oh, this time he's a... what's this? Timothy's a hawk again. He's got another 6. Hey, you're not doing too well. It's a problem. I know what you were thinking. You were thinking, if you both play hawks, then you'll build up a score, negative score of -2s. And so you were thinking, why not both play doves? Because you're a dove-like person. And then he cheated. He went and played the hawk each time. You see, it's very tricky to know what to do in this kind of game. Add up the scores. So what's that? 0 to Owen and 12 to Timothy. Okay, give Timothy a hand. Thanks very much. Okay. Well now, is this anything more than just an amusing game? And the answer is yes, it is. It's part of quite a serious mathematical model to try and explain the evolution of animal conflicts, the logic of animal conflicts, and the evolution of certain strategies in animal games, in animal behavior. You see, the problem is, take deer, for example. We've got a film of some deer fighting. Why do deer actually, why do deer fight the way they do? Here's a deer at rutting time. You can see him displaying there. And there's a couple of deer pushing against one another, you know. They have to bend down and put their antlers together and just shove backwards and forwards. Now, there they're displaying, just displaying again, you see. Now, this is really a most inefficient way of fighting, because if a deer really wanted to win the game seriously, he'd creep up behind his opponent when he wasn't looking and then try and chase him. Well, I mean, his opponent was looking, he saw him. So he'd really, if he really wanted to be efficient, he'd tiptoe up behind him and then pierce his flank when he wasn't looking. You see, how is it that deer have evolved this highly inefficient strategy of putting their heads down most of the time and just pushing? Well, other animals don't even touch. They don't even touch. For example, take a baboon here. Here's a picture of a baboon. Well, he looks quite fierce here, but when we see him in his habitat up in a tree sometimes, there he looks as if he's yawning. But in actual fact, this yawn here, which looks so innocent to our eyes, is a very fierce display gesture, establishing his dominance and threatening his rivals and saying, if you don't give me right of way, then I will really bite you. So this is a display procedure where he doesn't actually touch. Or another example is a blackbird. Here's a blackbird, and you can hear. Can you hear the blackbird sound? Here's a singing blackbird. Well, of course, one's first human reaction is to say that this is a very beautiful sound. But in actual fact, it's a territorial right song. What he's actually saying is to other blackbirds, don't you dare come into my territory, otherwise I'll bite you or fight you. But he doesn't actually fight. He only stands up and does this ritualized display. Well, what we've got to explain is how animals develop this ritualized display rather than serious fighting. I'm talking mostly about animals of the same species, I mean 2 male blackbirds or 2 male baboons or 2 male deer who are fighting for mates or for territory or for dominance in their hierarchy. Well, what Maynard, Smith and Price did was to abstract the essence of the idea. Of course, any mathematical model is an oversimplification, but what he wanted to try and do was to get the essential point which would explain why these rituals evolve. So the first thing he said, let's suppose this animal has three possible strategies, three possible courses of action: escalate, the fight, or display, or run away. So a very simplified version. Now, let's imagine we have two types of animal, hawks and doves, and the hawk strategy will be always just to escalate the fight. And the dove strategy will be to display until your opponent escalates and then run away. See? And now the next thing to do is to award them payoffs. You see, here's a payoff. This is the list of payoffs. I mean, imagine when a hawk meets a dove, the hawk will win, you see, and so we'll award him a score of +6. But now imagine two hawks meeting. They will immediately escalate and fight until one gets injured. And then we should award 6 to the winner and -10 to the injured party, because an injury will not only knock him out of that fight, will probably knock him out of the 3 next fights too. So it's a very bad thing to have an injury. That's why we penalize him much more than this +6. Now let's imagine two doves coming along, and when they fight, they just go out into a display, and they display for hours against one another. Nothing will ever stop the display. Meanwhile, a third party comes along and takes off the female, and they go off together, you see, while these two are still displaying. So it's obviously a disadvantage to display too much. So we give them a small penalty, -1 for wasting time. Okay. I mean, what do these numbers really mean? They don't really mean, the actual size of the numbers is unimportant. The model will be qualitatively the same as long as the middle number is bigger than the top one, which is bigger than the below it. As long as you have them in the order 10, 6, 1, then any numbers will give you the same kind of model. And what these numbers really mean is that if you get a positive score, then you will get more offspring, and therefore your children will be more likely to survive. Well, now we can prove this. We can prove this payoff matrix now is actually a theorem, because supposing two hawks meet, then there's a 50% chance of winning, so we give them each +3, and there's a 50% chance of getting injured, so we give them each -5. So +3 -5 is equal to -2. See, now you begin to see why it's so bad to be a hawk, because you're liable to get injured. Now, let's see, if a hawk meets a dove, then of course he will escalate, and the dove then will run away. And so the hawk will win, so he gets a good +6, and the dove gets 0. Now, if two doves meet, then what will happen is they'll go on displaying, so each of them has a 50% chance of winning, so we give them each +3, but then we penalize each one of them -1 for wasting time, so it comes down to 2. So now we have, you see, why I used that particular payoff matrix in the game that we did just now. Well, what will happen then in the long run? And the answer is, we can now prove quite an interesting theorem that in the long run, the population will evolve to 2/3 hawks and 1/3 doves. You see, why should this be so? Supposing the population was all hawks, then which is the better strategy to play? If you were a hawk, you'd get -2, but if you were a dove, you would get 0, which is a higher number, so it would be better to be a dove. You see, what happens is, every time you meet a hawk, you run away, so you live to a ripe old age and have lots of offspring, while the hawks are busy killing themselves off. So eventually you have more offspring, you see, and therefore it's an advantage to be a dove. Now, if you had a population of all doves, then obviously it's a much better strategy to be a hawk, because you'd win every fight, whereas the doves would be only getting 2. So neither to be all hawks is best, or to be all doves, so somewhere in between is best. And this is the exact point in between which is best. Well, now, before I prove this theorem, I want to play the game with you to illustrate why this particular proportion is a stable proportion of doves and hawks. So I want you all to play the game with me. You see, I will play 2 hawk plays and 1 dove play to represent a population of 2/3 hawks and 1/3 doves. Meanwhile, I want each of you to decide in your own minds whether you want to be a hawk or a dove and stick to that decision and play 3 goes the same. So, are you ready now? We're going to have 3 goes. Okay, all point at me. That's right, all point at me, gaze into my eyes, maintain the poker face. Are you ready? Now, 1, 2, 3. Now, all you hawks get -2 because I played a hawk, and all you doves, precious few doves, there's a dove, you get 0. All right, start again. Ready? 1, 2, 3. I played a hawk again, so you double what you had previously scored. Right? Now I'll play again, once more. Ready? 1, 2, 3. Now this time I played a dove, so the hawks get 6 and the doves just get 2. Now, by right, what score did you get? 2. Yes, everybody got 2. You see? That's the unique proportion where everybody's score is the same. You see, therefore, because there are 2/3 hawks and 1/3 doves, everybody will have the same number of children, so there'll be 2/3 children, hawks, and 1/3 dove children, and therefore the population will remain exactly the same. Well, all right, now we know once it gets there, it'll stay there, but how does it actually get there? So I must prove how the theorem, how it gets there. So we start off with a 2-dimensional graph. Along the horizontal line, I'll mark the proportion of doves in the population. Along the vertical line, I'll mark the proportion of hawks. You see, so this red spot at the unit point represents a population of 100% hawks. And here we have 100% doves. And this point, midway in between them, would represent half hawks and half doves. And all the various points on this line would represent the various possible proportions. So all the part of this graph that we really worry about is this line, because this represents all the possible proportions of hawks and doves. So we don't need the whole graph. We'll just take that line off and throw the graph away, because that's the only bit of the graph that we really need, you see. Because the next thing I want to do is to work out the advantage of playing various strategies in various different populations. You see, here's this long line here. That's all hawks. Now, if it's all hawks, and you go and play the hawk strategy, you'll get -2 every time. And if it's all doves, and you go and play the hawk strategy, you'll get +6 every time. And any proportion in between will be covered by this straight line representing the hawk strategy. See, so that straight line represents the advantages of the hawk strategy. Now, I want to put on this graph the advantages of the dove strategy. If in a hawk population you play dove, you'll get 0. But if in a dove population you play dove, you'll get 2. So the dove strategy is this green line joining 0 to 2. Now these 2 lines cross at this point. And if I drop that down there, I get exactly the point A, which is 2/3 hawks and 1/3 dove. It's a distance 1/3 from the hawk end. And now you can see what will happen. If you're to the left of this line, then it's better to be a dove. And so the doves will have more offspring, and therefore proportions of doves will increase, so you will move towards the point A. So I will put a little arrow indicating that you will move towards the point A. Now, if you're to the right of A, then the hawk strategy is better. And therefore, the hawks will have more children, and therefore the proportion of hawks in the population will increase, and so you will actually move to the left. And in both cases, you move towards A, which is therefore an attractor point. That's what A stands for, attractor. And so on my model here, at exactly a third of the way along, I'll put a black point for the attractor point and 2 black arrows there, moving towards this to indicate that that point is an attractor point. So what I've done is I've replaced my theorem that there were 2/3 hawks and 1/3 dove by this picture. Well, you can say, well, that's rather a lot of fuss to reduce everything to a picture, but that's because I will now reveal the full Maynard-Smith and Price game. You see, they included not only hawks and dove, but two other kinds of strategies, the bully and the retaliator. You see, remember, this is what you do first. This is what you do if the other guy escalates. Well, the hawk just escalates right away, no trouble. The dove displays, and then if the other guy escalates, he runs away. Now, the bully, he escalates first, has a go, but then if the other guy escalates, he runs away. So he does exactly the opposite. You see, to a dove, he appears like a bully, and to a hawk, he appears like a dove. To a dove, he appears like a hawk, and to a hawk, he appears like a dove. Now, the other guy, the retaliator, he first of all displays, but then if the other guy escalates, he escalates too. So he behaves the same as the other guy. He behaves like a dove to a dove and a hawk to a hawk. So now we've got to work out the full payoff matrix for 4 strategies. So this will be our next theorem, theorem 5. This is you, and this is your opponent's strategy. And this is the payoff to you. Well, the first little corner is exactly what we had before. And now let's see what happens when a hawk meets a bully. They both escalate, and then the bully runs away immediately. So the hawk wins, and the bully loses. No waste of time. Next, when a hawk meets a retaliator, the hawk escalates. First of all, the retaliator displays, but then the hawk always escalates, and so the retaliator escalates, and then they both behave like 2 hawks fighting, so they both get -2. Now, what happens when a dove meets a bully? The bully escalates, so the dove runs away. So the dove gets 0, and the bully gets 6. Now, what happens when a dove meets a retaliator? Well, they both go on displaying. They both go on displaying for hours, so we penalize them for wasting time, just like 2 doves. Now, what happens when a bully meets a bully? Well, they both escalate, but the first one to escalate, the other one runs away. So there's a 50-50 chance of winning, so they both get 3, and there's no wasting time at all. So we give them 3. Now, this is an interesting one. When a bully meets a retaliator, see, the retaliator displays, then the bully escalates, so the retaliator escalates, so the bully runs away. So the bully gets 0, and the retaliator gets 6. And finally, when 2 retaliators meet, they just behave like a couple of doves, and so they just display 2. Well, if you look carefully at this matrix, that you find there's no advantage to anybody at all. But let's see if we can prove the corresponding to theorem to this. So, but it's going to be difficult to do with 4, so let me just start with 3. So I'll just take the hawk, the dove, and the bully. So could we have 3 axes? See, this time I've got a red axis marking hawks, and that's the unit point representing a population of all hawks. Here is a green axis marking doves, and so that's a population of all doves. And here's a yellow axis to symbolize the bully, and that's a population of all bullies. And this line at the bottom represents mixtures between doves and hawks, and here would be mixtures between doves and bullies, and there's between bullies and hawks. And all the points in the triangle here would be mixtures of all 3. Well, you remember, the first thing to do is since you're only interested in that triangle, we can throw the axes away and just stick to this triangle. Now, how do I actually put arrows on the triangle? It's a problem. You see, you remember I said right at the beginning we had discrete things behaving discretely. Well, individuals, when they're fighting, are discrete things, and these strategies mean they are behaving discretely. But when we pass to populations, the strategies in the populations are discrete things. We've got 4 different strategies, so we've got 4 discrete things. But the fact that populations can grow, wax and wane, means that they're behaving continuously. So we've got to switch our style of modeling. We've got to switch from probability and game theory to calculus and differential equations. And this has only recently been done, having evolved the mathematical differential equations from game theory. And what I'm going to show you now is not yet been published. It's just recent research. And some of the theorems about such flows have only been discovered in the last few months. Well, when we do the differential equation and solve it, we get some flow lines on the triangle telling us how the population will evolve. And the first interesting thing to notice is that that point there, which originally was this attractor point between hawks and doves, now has a flow line coming out of it. That means that if a mutant bully appears, then that mutant bully will invade the population and cause you to swoop towards this point. And so the population will now evolve to a mixture of hawks and bullies, and the doves will be completely wiped out. So, now we know what happens when 3, we must go to 4. And now we need some 4-dimensional axes. Have you got some 4-dimensional axes?
We couldn't make them.
Well, it's all right. As you know, as you saw, we don't really need 4 dimensions worth of axes because, you see, we can take the unit points on each of the 4 axes, join them up with a 3-dimensional tetrahedron, throw the axes away, and here's the tetrahedron. So, and you can see, this face of the tetrahedron is exactly the same as what we had before, namely the flow lines flowing towards this black point, which is the attractor when you've got just hawks, doves, and bullies. But now, when we introduce retaliators, we find that out of that spot, that's no longer a attractor because there's a flow line coming out of it. And all the flow lines swoop then towards the retaliators. So if we examine the retaliators carefully, you can see, what you've got to do is you've got to imagine the whole of this solid tetrahedron completely filled with flow lines. Not only the ones I've drawn on the faces, but the flow lines in the interior. And they're all swooping towards this retaliator point. You see, if I have a mutant in this direction, then the flow lines take me back. Or if I have a mutant in this direction, this one here, then the flow lines take me back this way. Or if I have a mutant here, the flow lines take me back this way. So this is well, apart from a point which I'm going to mention in a moment, this is an attractor, and this explains why the strategy of retaliator is a very good one from the point of evolution, because as soon as a retaliator appears, as soon as that type of strategy appears ingrained into the mind of an animal, and if you assume, too, that retaliators' offspring are retaliators, hawks' offspring are hawks, and so forth, what this mathematical proves is that the retaliators will evolve by Darwinian selection. They will have more offspring and finally wipe out all the other types in the population. So that explains, or this offers one type of explanation of why so many species have evolved the display technique. And if you look at yourself, I mean, when you go around amongst strangers, you behave very, very politely, but if a stranger starts being aggressive towards you, then you feel a surge inside yourself, this archaic instinct to retaliate back. So it's possible that this type of model might give an explanation of some of the instincts that human beings have inherited from our animal forebears. But now let me return to this rather interesting line along the retaliator dove axis. You see, if we go back to if you remember the payoff matrix, when retaliators meet doves, they just display to one another. And therefore, there's no advantage being a retaliator or a dove. And so there are no arrows along this line at all. And therefore, you can have genetic drift along this line. So if you get a population of retaliators, then they will tolerate the emergence of doves. Indeed, if you get a mutant bully appearing along here, a little mutant bully, then he will soon be stamped out. But as a result of his stamping out, the population will have moved a little along this retaliator dove axis. So they will begin to move a little bit in this direction. Every time a mutant hawk appears, you'll drift along this axis until you get to this point. And at this point, something tremendous will happen, because when the mutant hawk, that red hawk, appears here, suddenly he will invade the population, whoosh, and he will stamp out all the retaliators, and the population will evolve to just hawks and doves. And then, of course, whoosh, the bullies will appear and stamp out all the doves. And then, of course, whoosh, the retaliator will come back in again. You see, so this whole complicated cycle of events will take place again. Well, of course, whether or not this does take place means we shall have to go and take this theoretical model, which has been proposed by theoretical biologists, and then the flow lines have been adapted by mathematicians. We'll now have to go back to the experimental biologists and ask them, can you observe this kind of behavior in evolving animals? And of course, it's also tempting to ask whether or not you can extend this model from animals to actual social behavior. Of course, very dangerous this is, very dangerous to take a theory from one field of knowledge to another field of knowledge. But if you did extend it to human behavior, and instead of evolution, you had social pressure, and instead of fixed types of hawks, doves, and things, you had proportions of behavior within yourself, then this little story that I've told of retaliators evolving and then a mutant hawk causing a revolution, killing off all the retaliators, then you have a mix of hawks and doves, and then a mix of hawks and bullies, and then a dissident coming along, whooshing back to retaliators. This might be a story of actual social life in some social societies. However, that, of course, has to be examined very carefully, and that would be a very speculative, tentative theory as yet. But I hope that this idea of game theory and the idea of switching from game theory to modeling evolution will give you a picture of the first two types of modeling that I first talked about. The first two styles of modeling, the discrete things behaving discretely and the discrete things behaving continuously. And in the next lecture tomorrow, we shall do continuous things behaving continuously, the waves, and then the continuous things behaving discretely, the harmonics. And in the last lecture, we shall do the catastrophe, the continuous things behaving discretely, unexpectedly. Well, thank you.
The desk. I can get a still photograph of you and
Okay.
it's far away from me.
if you can all just listen intently, because we want a few shots for editing of you listening. We'll look as if you're paying attention.
Well, shall we?
They're laughing.
No, you want to think about something serious. Now, I'll repeat to you 1 to 10 in Russian so you can learn it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm afraid I don't have a very good accent. That's wrecked.
English and Japanese.
Oh, dear.